Hey guys, it's Sven. In this video, I'll show you some different activation functions that can be used. I'll show you the advantage and the when we should use them. I'm going to show you 5 of them, but the softmax is the one that is like a little bit more complicated. And I will show that to you in the next video. So let's get started with the Sigmoid that you already know, and it looks something like, well, you probably know how it looks. It looks like it goes from 0 to 1, and it's always in between, and it looks really soft. This is like it's pretty good. We used it before, it worked for us, but there are a lot of disadvantages, and there should be a video from me about the gradient vanishing problem, and it's one of the hugest problem, or it's like one of the biggest problems that exist in your networks. For example, when you make a bigger network, it might happen that the gradient or the error signal in the beginning of your network just like completely vanishes because the error is always multiplied with the derivative of the output. And I've prepared something on the web. I'm going to show you that, and it's the Sigmoid function. And it looks something like this if you graph it. I'm also going to show you the derivative of that, and it looks something like this. So this red line, and you see that the maximum of that is around 0.25. So whenever we go one step back in our network or one layer back, and the maximum derivative that we can reach with our function is 0.25. So our error signal is, if it's like the best case that we could have, it is divided by 4. This means that, let's say we have 2 layers, the error of the first layer will be like so little that it will pretty much not exist anymore, and therefore the wakes will not update as expected. So how could we solve this? We would need a function where the gradient is, or like the derivative is much closer to 1. So I'm going to show you an alternative for that, and it's the TanH function, and it looks something like this. So f of x is TanH of x. Right now we are going from -1 to 1. So we're not from 0 to 1 anymore, but from -1 to 1. And this is better. For example, the derivative of that is 1 minus TanH squared. And I'll show to you this one as well. So I'm going to remove this for now. And I'm going to show you this. Well, I'm also going to show you the sigmoid. So you can always see that it's much steeper in the middle. And actually the derivative at 0 is equal to 1. So I'm going to compare the derivatives of those. So this is the derivative of the TanH, and this is the derivative of the sigmoid. So the TanH is way better to avoid gradient vanishing, but it could still happen with bigger numbers. Therefore, there's something very simple that has been introduced a few years ago, and it's the ReLU function, and it looks something like this. So that's very simple to calculate. It's either 0 if we are below 0, or it's like x if we are above 0. And the function is simply max of 0 and x. And the derivative is also simply like, if we are above 0, we have like a derivative of 1, and if we are below 0, the derivative is 0. There's a huge problem with this, or well, actually, this function is pretty good, but for example, we can reach infinity with this, which is okay. I mean, it depends on, do you want to reach infinity or not? But the problem is that it might happen that you get below 0, and if this happens, the derivative will always be 0. Now let's think about this. You have a network, and you're doing the first training step, and all your weights are like modified that they go below 0. So every weight is, let's say, -1 or -2 or whatever. And your sum in your fully connected layer, for example, right now, the sum will also be negative because of that. And if the sum is negative, your derivative will be 0, and you can't change it anymore, because when updating the weights, we need to multiply it by the derivative. And yeah, that's like a problem. It's called the dying ReLU problem. It just happens if the sum gets below 0 and there's like nothing that could bring that output neon. Like the neon really dies. That's like the neon just dies. The output is always going to be 0. It can't change anymore. Those weights are pretty much lost. And yeah, like there's nothing happening with that neon and those weights anymore. Therefore, there's an idea to not have a derivative of 0, but to have a derivative that is a little bit um, bigger than 0, and it looks like this, and it's called the Leaky ReLU. In here we have got a parameter, and it's exactly the same when we go above 0, but below 0 it's simply ax instead of 0. So we will have a like slope down here, and that's pretty much the Leaky ReLU. And the derivative looks pretty similar. It's 1 if we are greater than 0, and it's a, like this parameter, if we are below 0. And this parameter, it can be chosen, like you can choose it however you want. I've chosen in my network, I think 0.01, but that's like up to you what you choose. And this is already it. Oh no, this is not already it. Like the ReLU and the Leaky ReLU, they avoid gradient vanishing because the derivative is always 1, or pretty much always 1, unless we get below 0. So this means that let's assume that our output is always greater than 0. There will the gradients will not vanish because the error signal will always be multiplied by the derivative, which is 1 or like maybe 0, but it's usually 1. So the gradients will not disappear. And this is really important. And with this, we can build way deeper networks, like networks with 8, 9, or 10 layers, which would be impossible with a Sigmoid or TanH function. And yeah, this is like pretty much what you usually go for right now. When you see any paper or something like that, they're using the ReLU. It's easier to calculate. It's like faster for the PC, but that's not the main advantage. It usually is like the gradient does not vanish, and that's really amazing. And in the next video, I'm going to show you the softmax function, but that's a little bit more complicated. So I have to see you in the next video.